Hi, everybody. Today we're going to do section 2.9, which is applied optimization. So let me just share my screen and let's jump right into. Oops, that's not what I want. Here we go. And here we go. Section 2.9, applied optimization. And so let's look at the example here. A manager of a garden store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built of redwood fencing at a cost of $7 per foot, and the 4th side will be built of cement blocks at a cost of $14 per foot. Find the dimensions of the least costly such enclosure. So first of all, let's see if we understand what does that even mean? The dimensions of the least costly enclosure. All right, so here's the 3 sides that are red, and here's the 4th side. So I'm going to call this side X. Now, if this is X, the other side is also X. It's a rectangle. The opposite sides are equal. We'll call this side Y. And if this is Y, of course, the bottom is Y. The first thing they're telling us is that the area is 16. So that means that X times Y equals, I said 16, I meant 600. The area is 600. The area is X times Y. So the area is 600. That's the first fact that they're giving us. The second fact they're telling us about the cost. They're telling us that they're telling us that the 3 sides, these 3 sides, in other words, 2x plus 7, this amount here comes out to $7, is $7 per foot. And the 4th side, which is side Y, that comes out to $14 per foot. But in equation form, that means that that should be Y, by the way. That in equation form, that means that 7 times 2x plus y, meaning I take $7 per foot times the amount of feet, plus 14 times y, there's $14 times the length of this wall. That is that's not necessarily equal to a constant amount of 600. That's just some number. We'll call it C. C for cost. C equals cost. So we want to minimize C. So C is a function of 2 variables. C is equal to 7 times 2x plus y plus 14y, which of course that equals, let's see, 14x plus 21y. So, who wants all these variables? I don't want all these variables. I don't like so many variables. So what I'm going to do is I'm going to make a substitution in order to get rid of some of these variables. Now, if you remember up here, I had this information that xy equals 600. I haven't done anything with it. So I'm going to solve for y. Y equals 600 over x. And what I'm going to do is I'm going to take my 600 over x and I'm going to substitute it in for y into this equation. So C is equal to 14x plus 21 times 600 over x. And the advantage of this is that now I have a function of just one variable. So C is just a function of one variable, and now I just want to find the minimum. Well, we're going to find the minimum the same way we did when we were sketching curves. We're gonna look to see when the derivative is equal to 0, and do all the different tests and so on and so forth. So let's just get the derivative. Let's get C prime. So C prime is equal to, that's just 14 plus, well, let's see, 21 times 600 is 12,126. Let me just double check that math. 22, I'm just double checking the math here. 21 times 600 should be 1, 2, should be 1, okay. So the derivative, so this is equal, 21 times 600 is 12,600. The derivative of 1 over x is negative 1 over x squared. And that's an example we've seen a bunch of times. Just as a side, I'll tell you where I got that from. So so c equals, so let's say we have let's just take the derivative of the d dx of 1 over x. That's the same thing as d dx of x to the negative 1. So it becomes, so it equals negative 1 times x to the negative 2. That's the same thing as saying negative 1 over x squared. Okay, now we want to set this equal to 0. Well, very nice. Since that's a negative and that's a positive, I'm going to bring this over to the other side. And I get 14 equals 12600 over x squared. And that means that x squared, I'm going to equals 12600 over 14. In that, what does that equal? That equals 12600 divided by 14 is 900. So x equals plus or minus 30. Well, I could get rid of the negatives. I can get rid of the negative 30 because we're talking about a physical object. You know, that's the difference, by the way, that's the difference between a mathematical, you know, it's funny when we're dealing with mathematical equations, then you know you may have, when we're dealing with mathematical equations, you may have you know, a negative number in your answer, but you know, we're going to discard that now. So 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 we're going to discard this, and we're going to say x equals 30. Now I just want to test, is this a min? We want this to be a min. So we can take the first derivative test or the second derivative test. I think I'm going to take the second derivative test. It's kind of easy in this case. So c double prime. So the derivative of 14, let's just look up here. The derivative of 14 is just 0, so it disappears. The derivative of this is going to be positive. Well, again, let's rewrite this. This is, I want ddx of negative 12600 over x squared, but that's equal to ddx of negative 12600 x to the negative 2. So it's going to become a negative 2 times negative 12600 times x to the negative 3. And that comes out to be, let's see, 24, 126 plus 126 is 252. That's going to come out to be positive 252 over x to the third. And I just have to test it when x equals 30. I just have to test it when x equals 30. So c prime of 30 is equal to 25200 over 27000, which, I mean, the truth is, it's all I care is that if it's positive or negative, and this is clearly positive. It's a positive number divided by another positive number, so it's greater than 0, and that means that the function is concave up at 30, and concave up means I do indeed have a minimum. So we are good to go. And I definitely have no problem. 30 is definitely part of the domain. It doesn't make any fractions equal 0 or anything like that. So I see that my answer is going to be x equals 30. X equals 30. Now let's just remember what the diagram looked like. Well, actually, forget the diagram. Well, I don't need to revisit the diagram. All I need to do now is figure out y, and I'll use the equation that xy. I'm going to use xy equals 600, which means 30y equals 600. So y equals 20. So I have, and that's my answer. That x is 30 and y is 20. And those are the dimensions. So the dimensions here is going to be a 20 by 30, 20 by 30 a rectangle. And let's just actually check the answer, because I know that 20 times 30 equals 600. That part I know. But I want to check. Let's see. I'm sorry, I don't mean check the answer. What I mean to say is let's see what the actual cost is going to be. That's what I meant. What's the actual cost is going to be? So the actual cost, whereas we know the dimensions, let's find the actual cost. Let's see, and it's better be in the budget because it's the smallest amount, so it better be in the budget. Okay, so the actual cost is equal to 14x plus 21y. And let's see, 14 times 30 is 42, 0. And that's going to be plus, wow, 42. That's amazing. Wow, that's amazing. 14 times 3, 20. That's amazing. Um, that is very amazing. So, and which, of course, equals 840. So this is going to cost you $840 if you to construct a wall in this manner, and that is a beautiful thing. Now, I think what I want to do next is I want to graph this in Desmos just to see that in Desmos, I want to see that Desmos backs us up. So I'm going to share my screen. I'm going to go into Desmos. Let's get Desmos here. Now I need to switch my camera. Okay, we have, and we're putting in y, C, well, I guess I'm putting in C. C equals 14 plus 12600 over x squared over x. That's my original function. And now you don't see it, do you? Just B because it is too high up to see. I think that this is 30. Let's just see. Let's see how high we gotta go, because you have to go all the way up to 840, so it's gonna be a while before we get there. That's interesting. That is interesting. I just noticed I made a typo. That should be 14x. Now let's see what happens when x equals when x equals 20. So let me so when x equals 30, the cost is 840, and that is the let me bring this down this more. Perfect. And let me just okay. Very nice. Let's go. Let's go on to let's continue. The problem that we just did is an example of the max min problem or optimization problem, whatever you want to call it. So sometimes we call it applied optimization, sometimes we call it max min problem, max min story problem. But the bottom line is that we have a situation we want to find, we may want to find a maximum, a minimum cost or a maximum revenue or a maximum area or a minimum. Sometimes in industry, if you when you're manufacturing things, you want to find minimum um, minimum resources used. If I'm going to make metal cans, I want to be able to make the biggest the cans that hold the most, but have um, the smallest amount of metal in them, and so on and so forth. These are the sort of problems that that these techniques will work, and they pretty much boil down to what we did. So let's just we'll go through step by step. So first, we want to translate the English statement into a problem, line by line by line, and draw a picture if possible. It may not be possible to make a picture, but draw a picture, and we want to like work this down line by line. We're going to want to eventually get one or two equations, but these equations are going to be play different roles. So we're going to identify the objective function. We're going to look for the words indicating largest or smallest. So if you seem to have two or more variables, we find the constraint equation and think about the English meaning of the word constraint, remembering a constraint equation will also have equal signs. And we're going to solve now in our example, in the example that we just did previously, xy equals 600 was the constraint equation, and what was it, 14x plus 21y? I think that's what it was. It was the cost equation was the objective equation. So that is our objective, is to find the cost. So we solved the constraint equation for one variable. In our case, we solved it for y in that previous example we just did, and we substitute that into the objective function. And now we have an equation with one variable. Once you have an equation with one variable, that's when you finally use calculus to find the optimum values. You take the derivative, find the critical points, so on and so forth. Check the endpoints, of course, so on and so forth. And we look back at the question to make sure you answered what was asked and translate your number back into English. So that's this is a summary of the techniques that are used for this sort of equation. This is the end of part one. I'm going to continue now. I'm just going to do more and more examples and explain it more and more. And this is the end of part one. And next video is going to be part two on the same topic, 2.9. Okay, everybody, it's been loads of fun. Bye bye.